Once we have a quantum dot, we can start thinking how to define a qubit using the charges in that quantum dot. We're going to do this in several ways, and in order, we will focus on the different parts of it. First, I want to focus on the different types of quantum dot qubits. Here you see a not complete overview of the possible qubit types using quantum dots. And you can see that here already 4 types of different versions that we'll briefly discuss. There are actually quite a few more of that. Sometimes this is called the zoo of the quantum dot qubits because there are so many different variations possible. Why? Well, quantum dots are very versatile, and so there's opportunities to think of how can we best operate the device, how can we best mitigate coherence. The loss di Vincenzo, and I will focus on this a bit more specific later on as well, but it's usually been seen as a single spin qubit. So we either have a single electron or a single hole, and in a magnetic field, and these the spin states are spin splitted by the Zeeman energy, and then the spin down and up state define the basis states of our qubits. And this can be either for an electron spin or a hole spin. And then we can try to think of ways how to control that qubit. This type of qubit is very elegant. It's almost the prototype when one thinks of a qubit, of a 2-level system. It's also been defining the state of the art today. Why? Because it's so easy to implement. A single quantum dot is sufficient to make a single qubit. It's also highly efficient and flexible. For example, one can displace a single electron spin through a series of quantum dots to transport quantum information. And this is also very useful in building quantum systems. So this is still the main workforce. At the same time, I also want to underline the statement that thus far the field has been focusing on few quantum dot systems. And then of course it's a very important question, how can I get the most out of my system? And that's true if for every electron we have 1 qubit. If we're going to larger systems, there may be different questions which become relevant. For example, the power dissipation. Which system will have the lowest power dissipation? And there are people that would argue this is going to be the driving force in the end, dictating the future development. The quantum dot hybrid qubit, the singlet triplet qubit, triple dot qubits, these are all versions that in principle can be driven all electrically, sometimes very fast, such as in a quantum dot hybrid qubit. And so these qubits may become more powerful when no longer the number of quantum dots is limited, but maybe the number of energy consumption that we can afford. Additionally, these qubit types sometimes provide a different sensitivity to noise in our environment. For example, by using 2 particles, one can become lesser sensitive, for example, for global noise and try to mitigate that, such that only local noise becomes relevant. And so depending on the development of the materials, the devices, which source of noise is relevant. Is it local noise? Is it 1/f noise? Is there correlation between the noise? What's the power dissipation to control a qubit? How fast should we control a qubit? Will dictate which qubit will be the best of choice. Thus far, we've been mainly focusing on single spin qubits, and we'll keep doing this. Why? One can also argue that a single spin qubit is in a way the basic ingredient for all these more advanced qubits. And so it makes sense to still focus on the essential part, and that's the single spin. How good can we manipulate these single spins? But as we'll see, also this can be done in various ways.